I'm going to. Right, so today I'm going to talk about Graphons. This is work which Shensu is also at Data 61. So what are Graphons? Graphons are graph limits. So we are here when we're talking about, we are taking a sequence of graphs. We have a sequence of graphs, and these graphs are growing bigger and bigger and bigger and bigger. So you have a sequence of graphs, and the number of nodes, it's going to infinity. And what we do is, for each graph, we look at the adjacency matrix. This is the adjacency matrix. We scale it to the unit square. And we color the so little blocks that are 1, and we leave the zeros as white. So those are the, so this is an adjacency matrix, say when there's like 15 nodes or something like this. And if the graph grows and have more nodes, like say 100 nodes, the dots become like very, like, small. But then the thing is, because we are mapping it to the unit square, we still have this like a pixel picture. And then you add more nodes, it gets noisy and so on, and you can see if these pixel pictures converge to something, right? So that's the idea, that's the limit. If they converge, there's a limit, and that limit is called the Graphon. So this is for Erdős-Renyi graphs, where you have like a set of graphs is a graph has n nodes, and each two nodes are connected with the probability p. Edge probability is p, so it is like every edge you toss a coin with probability p, and it's either connected or not. So for Erdős-Renyi graphs, these pixel pictures converge to the constant Graphon, whatever that p is. This is slightly different. This part is if you have it's a uniform attachment graph where the nodes here are more likely to have edges, and the nodes here are less likely to have edges. So that is, you have a function over this unit square. So you have a unit square, you have like some kind of function. And the thing is, these values are going to be between 0 and 1, because it is like, in effect, an edge probability. For the bipartite graphs, this is like, the actors and the films, where an actor acts in a film. So no two films are connected, no two actors are connected. Actors have connections with some films. So you can present it like this, and then it can go like this. But for a bipartite graph, depending on the node ordering, you can also get something like a checkerboard pattern as well. So depending how you order your nodes. Of course, if you order all your actors from here to here and all your films through there, you'll get that one. But then if you order your nodes in a mixed way, you're going to get something like that, and which is also in a way convergent to that. So that's the Graphon. And how is, this is the sequence of pictures converging, how is convergence done? So there are two methods that convergence is done, which are equivalent. The first method is the more graph theory method, which is called homomorphism density convergence. Basically, that is looking at motif densities, right? So you have, say, for example, if you have your sequence of graphs, so Gn is a sequence of graphs where n is the number of nodes. And if your f is an edge, so you can see what the edge densities are. Does the edge densities of these graphs converge to something? Then you can look at the triangle densities. So the edge density is 2 times the number of edges divided by n squared. You can look at the triangle densities. So to do the triangle densities, number of triangles divided by the number of all triangles that can be there, right, which is like roughly n choose 3, does that converge along the sequence? And you can see for different motifs where does that motif densities converge. If those converge, then that sequence converges to a Graphon. That is how convergence is defined, because this is, you have an increasing, the graph sequence have increasing nodes. So you've got to map these massive objects to a compact thing. So the method 2 is looking directly at the pixel pictures and seeing if the pixel pictures converge. So here we have, you have W1 and W2. So you have your W1 defined on a unit square. You have your W2 defined on a unit square. You see if W1 minus W2 goes to 0 along the way. Like for some W that's going to converge. This phi here is there to say, because these graphs, you can permute the nodes. You can like permute the nodes and like have a different graph. So you can, but you want to see on all the phi, are these two graphs the same, right? So that's accounting for these graph isomorphisms. That is why you take the infimum of all phi, where phi is this bijection. Yes, Jeffrey? Yes.
And so that's why your two checkerboard patterns in that first slide.
Yes, yes.
Yeah.
Yeah. It is not like, it is not exactly a unique thing. Like people want to make it unique things and sort by the degree or things like that, because it'll be easier if it was a unique thing, but it doesn't have to be a unique thing. Yeah. So the convergence in homomorphism density is equivalent to convergence in the cut metric, and this was proved by one of the papers from Boggs and Shane's group. So how can we use a graphon? Okay, say we have a graphon and we know all our graphs over time come from that. What's the use of it, right? Say we have the linked-in graphon, who's connected to whom. And if you have the graphon, you can say, if you want to generate a network of n nodes, you can say, okay, pick randomly n points. So you pick these points R1 to Rn randomly from the interval 0, 1. And for each Ri, Rj, you read this point, like you read what's the value of the graphon over there, right? So what is W, Ri, Rj, and that's the edge probability. And you toss a coin, and if it comes heads, you connect those two nodes. So for every two pair of nodes, you can connect it, right? And then you can get the graph. So you might see a sequence of graphs where there are 100 nodes, but you want to say, okay, how would the graph be if there are 200 nodes? Like, if you know the graphon, then you can connect it. And there are a lot of work done on graphon estimation from these graphs that are seen as well. So there are the graphs, you can have like dense graphs and sparse graphs. So dense graphs and sparse are properties of sequences that are the properties of graph sequences, not of a single graph. So dense graphs is if the edges are growing quadratically with the nodes. So you have, let's say Gn has n nodes and m edges. So if m divided by n squared, so that is like, it is like your edge density. So if m divided by n squared is always bounded, when your sequence as you go to infinity, if it is bounded by a positive constant, then those graphs are called dense. But if m over n squared goes to 0, that means your edges, because you've got m edges go subquadratically with the nodes. If it goes to 0, then that sequence is sparse. So that's not a sparse or dense is not a property of a single graph. It's a property of the sequence of graphs, right? So it's like how it grows. So this is like an example picked from a dense sequence, an example picked from a sparse sequence. Generally, if you pick an example from a dense sequence, there are lots more connections, lots more edges rather than in a sparse sequence, because the edges are growing subquadratically. So one of the issues with the traditional graphons is that graphs represented by this traditional graphon is either dense or trivially empty. That is, the problem is you cannot represent sparse graphs with these graphons. And why is that? The reason is this. So here we have a sequence converging to there. And if you take the integral or the area, if you have xy and wxy, and then take this volume that is under wxy, which is the integral, this integral converges to 2m over n squared. And for sparse graphs, m over n squared goes to 0. So for sparse graphs, if you keep plotting these pixel pictures, you're going to get the zero graphon there. And the zero graphon is not helpful, right? So the zero graphon is not helpful because say you sample n nodes and you try to connect them, like you have a WRIJ. So here, this is a zero graphon in this corner, but then it's kind of blocked. But so say WRIJ, you toss a coin, probability is zero, there's no edge. So you're not going to get any edges, you just have like n nodes, no edges. So, and that's not representative of a real sparse graph. Right? So that's the empty graph. So this is the problem with modeling sparse graphs using Graphons. Right? So this is the main problem. Like say, for example, for star graphs, so here we have the stars, we can see this. So here we have the number of nodes are increasing. And if we call the hub node, like, in every, say, we call the hub node node 1, we see here 1 is connected to everything else, but 4 is not connected to 5, right? So here, this part is all white, it's empty. Now, when you go n equals 20, this is 1. And then everything else is white, you have these 2 black bands. As n increases, these black bands get thinner and thinner and thinner and gets pushed to the corner. And when n goes to infinity, you're going to get just the empty graph, right? So when n goes to infinity, you're getting, that's the limit. And say you want to sample 100 nodes from that, you have 100 nodes, nothing is connected to anything. So you're not going to get the star back. So that's the problem of this, of the sparse graphs. So, of course, there are other non-Graphon methods that work with sparse graphs, like preferential attachment graphs, like Barabasi-Albert methods, where you have like this probability, like, a node comes in, and what's the probability that you're going to get connected to another node? You're more likely to get connected to nodes with higher degree, that kind of, those methods are there. The people have been, like, in a way, doing a lot of work on Graphons and sparse graphs because Graphons are very flexible. You're basically modeling the full adjacency matrix. You have a blueprint on the adjacency matrix, right? So because of that, there is, like, unlike having like one parameter, how are you going to connect to other nodes and not have a very strict thing? So the flexibility of Graphons has, I would think, like, there's more interest in pursuing Graphons or sparse graphs. So I'm going to go through some approaches. Sometimes this is, some of this work is a bit heavy. So, like, give it some attention, but don't give it all your attention, because I want to talk about the methods that we proposed as well. So the methods that are there, briefly, there's these Kallenberg exchangeable graphs that have been proposed by Caron and Fox in 2014 and others later. They're talking about like a different continuous exchangeable model rather than modeling graphs in a discrete way. Then there are these rescale graphons and stretch graphons proposed by Boggs and Shays and the group. And then there's this thing called edge exchangeable graphs proposed by lots of people, Crane and Dempsey, Broderick, Jensen, and the others. And another extension called GraphXs, which has like 3 things in there. And then sparsification as well. I'm going to go through one by one, like slightly briefly, but also, to give some idea. So Caron and Fox in this paper first proposed this method where their graphon is now defined on the full positive quadrant, right? So it's not on the unit square anymore, it grows. So it's a full positive quadrant graphon. And the way it happens is this: they have their nodes that come as a point process. So the nodes come as a point process in the 2D plane. It comes like this, but in the graph, if you just look at the graph happens like this. So let's say, so they have this parameter alpha. Alpha increases. So when alpha is in 1 and 3, that is, so alpha is between 1 and 3. Let's say you're drawing a box like that, then you only have that node. And 1 is connected to 1 here. Now, when alpha increases and when alpha is between 3 and 3.5, so you have this connection and that connection. So this works like an adjacency matrix. So you have here and there. So this node 3 is connected to, so node 3 comes and node 1.5 comes and they're connected if you draw a line here, when alpha is between closed 3 and open 3.5. Now, when alpha moves to 3.5 to 5, so when alpha is there, right, somewhere there, you have these 3 connections. So now a new node comes at 3.5, right? 3.5, it's connected to 1. So here, 3.5 is connected to 1. That's a new connection. And when alpha goes to 5, you have node 5 comes, but 5 is connected to 0.5. 5 is connected to 1, there, and 5 is connected to 3.5, and 5 has a loop here by itself, right? So the main thing here is their nodes are sampled not from discrete numbers, but from the reals. So you had the real line, they're sampling nodes from the reals, and you can sample in a way a lot more when you're sampling from the reals, and also coupled with they're defining the graphon on the full positive quadrant, they can model sparse graphs. Even with this methodology, if they consider a compact set, they said, if we consider the graphon to be compact, that is alpha is bounded, then we are going to get a dense graph. But if we let if we model on the full positive quadrant with this continuous sampling method, we can get sparse graphs, right? So that is of course, and they use like different theoretical properties of Kallenberg exchangeability to do this.
Is the on the red on the left side?
So yeah.
That's the graphon, right?
Mm-hmm.
This is the adjacency matrix. So they have these point processes coming here, right? So these are the point processes that come, and then this theta is the node index, and this V is the latent variable index. So the latent variable has a separate latent variable defined where that would be like in a way the graphon. This is the W where they define so if when say this point comes theta I, now you have another point here. Let's say so you theta I has a new I or a VI, and for VI and VI you go and you can see, like, you can toss a coin, and for VI VJ you can toss another coin. So that's the graphon. Yeah. And from there you generate all that. So this set of methods by Boggs and Shays and the group, so there's a lot of work done by Christian Boggs and Jennifer Shays and their research group. Here they have, this is the standard graphon where we are defining it on the unit square and the height is 1, right? But then they say, let's rescale it. We are, so for here we have the W is the edge probability. We don't need to have it for edge probability. We can let it go to infinity. So here they let the height go to infinity by rescaling the W. So the W is the original graphon. They divide it by the norm of W. So for a sparse sequence, this goes to 0, and you're getting your W tilde at those positions to be very, very high. So you're having these infinite mass at certain positions because these unit squares are going to 0. That's the reason. And you have to have more like measure theoretic rigor to get the stuff out of it. So that's what they're doing here. Then in this one, they keep the height as it is at 1, but then they say, oh, without having a unit square, let's expand the domain to the full positive quadrant. They do it by the original W. Inside x comma y, they have a square root norm of W. So this is going to 0. As it goes to 0, this gets bigger and bigger and bigger, right? then then there is this thing called edge exchangeability, because here, all these graphs have this property, what's called they're exchangeable. The vertices, you can exchange them. And they say the distribution is the same if you vertices exchange the vertices. But here, so in Crane and Dempsey's paper, they say we get a graph like this. This is the graph we get. It's our decision to either to label the nodes, which is what we are doing, and work with vertex exchangeable graphs. However, we can equally label the edges and work with edges instead. And they show, and then first Crane and Dempsey in these papers, and Kandanaarachchi and Towan, Broderick and Campbell and Jensen, all these people show if you do edge exchangeability, these you can model sparse graphs a lot easier. And then there are GraphXs originally proposed by Witt and Roy, where they have these three things. There is isolated edges, stars, and the standard Graphon. So they say so one of the things that I've seen that people say is it's the stars that's the problem. The stars are the problem. And we have a separate function to denote stars. And here in this picture, the green edges are coming from the star function. The blue edges, so the black edges are coming from the W. And there are some blue edges like that, which are the isolated vertices that is coming from I. So they have those, but then in their paper, they consider I to be 0 and S to be 0. Later, in this paper by Walsh and Chase and the group, they also talk about GraphXs, and then they say, oh, there can be like this skeleton of high degree vertices, stars, that are and then the rest can be low degree vertices which are modeled by the W. So the work we are doing has links with these as well, but slightly different. So, and then this is a method that's very commonly used in machine learning, where instead of having a single Graphon W, you have this sequence of Graphons Wn, where it is raw n wx comma y. So raw n is the edge density. So as the edge density goes to 0, so you start with the Graphon and you dilute it, and then you make it 0. So what you're sampling, because in a real example, you're never going to go until 0 and get the 0 Graphon, but you can get sparse and sparser graphs. But the problem with this approach is you can't generate large hubs. You can only get graphs that are diluted dense graphs. You can't get like these big hubs and everything everywhere else. So so just going over the common theme. So this is the problem where everything goes to 0. Extending the Graphon to the positive quadrant where it's non-compact. It's one of the ways to go. And then the modeling graphs as point processes. So modeling graphs on the continuous 2D plane instead of having on the discrete space. That's another way to go, but then they use Candanaarachchi exchangeability and more measure theoretic approaches. So all these things work on the directly observed graph. So what we are proposing is something slightly different. What we're proposing is, okay, this is the original problem. Let's transform the graph sequence such that the transformed graphs are dense. Right? So if we can do a transformation to G such that the transformed graphs are dense, then we are out of that problem. Right? That is what we are proposing. The method we are talking about works on a subset of sparse graphs. It doesn't work for all sparse graphs, though. That's the limitation. So what's the transformation? The transformation is taking line graphs. So line graphs are, you have your graph and you map the edges to vertices. So this is your graph G, and we have 1, 2, 3, 4 edges. So this edge is mapped to vertex 1 in your line graph H equals L of G. This edge is vertex 2, that edge is vertex 3, and this edge is vertex 4. 1 and 2, they share a node, so those edges are adjacent, so these two vertices are adjacent. 2 and 3, they share a node, they're adjacent, so that is adjacent. And 1 and 3, that is also adjacent. 3 and 4, there is an edge. So this is called the line graph because some time ago when Frank Harari motivated, he was doing graphs long time ago where he called vertices points and edges lines. So the term line graph, but it is such a not a good name, not a fan of the name, because it's difficult to kind of Google and you get like these time series type graphs and you Google line graph. So people have used other names: interchange graphs, edge to vertex dual, covering graph, derivative derived graph, adjoint conjugate. Computer scientists are using non-backtracking graphs. All these different names are there, but still the name line graph is like the standard one that people are using. So what happens with line graphs is this: when we have sparse graphs like stars, the line graphs of stars are complete graphs. So now, so here we can have the edge. Let's say this edge is this vertex mapped to this vertex. This edge is that mapped to that vertex. So these two are adjacent, so they are connected, right? But any edge is connected to any other edge to the hub vertex. So every vertex here is connected to each other. So the line graphs of stars are going to give complete graphs, and the complete graphs gives dense sequence of graphons. Right, so here the stars converge to wxy equals to 1. So you get dense. But now you might think, okay, previously we had all going to 0, now you have all going to 1, what's a big point, right? Like you might do like a complement. It doesn't work with the complement graph though, right? The point is, if you have like say 1 star, you're going to get like w equals to 1. If you have 2 stars, you're going to get 2 things like this. If you have 3 stars, you're going to get these three disjoint connected things, because these 2 stars, this node is not connected to any node there. So this would be one fully connected subgraph, and that would be another fully connected subgraph. So you're still getting the structure out without it going to 0. So you're modeling these. You're modeling these high degree vertices separate.
So sorry, what would the original have looked like for the 4 stars? What would the original have looked like? Just kind of 4 lines?
Yes. So you'd have.
What's wrong with that? What's wrong with just having 4 lines? It's not all white. You can still see a structure. What's wrong with that structure?
It gets thinner and thinner and thinner, and it's a measure 0 set. Okay. So when you sample, it's very unlikely you're going to, yeah.
Whereas if you just took if you took the complement of these graphs, then you would just you instead of it all going to 0, it would all go to 1, which doesn't help you anymore.
No, not for a single star. It doesn't. But but like say if you have something like this, you can. For a single star, but
even for these multiple stars, if you just took everywhere there wasn't an edge, you put an edge, and everywhere there is an edge, you get rid of it. Mm-hmm. Then the graphon for that is going. So
you mean the complement graph?
Yes, I'm saying the complement graph doesn't help you. But
no, and it's also the open question of when would you switch to the complement, like for complex structures that are a combination of stars and not, that decision of when to switch to the complement just to see things better would be unclear.
Yeah. So when does the line graphs give dense graphs? It is this particular condition that we call it max degree condition, which is, say we have a GN sequence of graphs. GN has n nodes and m edges. And if the maximum degree of GN is D max, n to say it comes from GN. So if D max divided by m is the number of edges, and if you look at the sequence, so for every GN, you take maximum degree divided by the number of edges, and if you look at that sequence, and that sequence is strictly the limit, or the lim inf is strictly positive, then that sequence of graphs, when you take the line graphs, they will be dense. So, this set we've called is S sub x. If the sequence is in S sub x, then their line graphs are dense. So if you take like for a GN in Sx, HM is the line graph. And then if HM converges to U is not zero. We can show that. So the line graphs are going to be dense, and that is that condition. So it is not every sparse graph does not give that condition. It is a subset of sparse graphs that gives that. It is like, so you have all your dense graphs here, you have the sparse graphs here, because there is this gray space where, because there are graph sequences that don't have converging edge densities, right? Say, for example, you take a dense sequence and a sparse sequence and mix it, it's kind of neither dense nor sparse. So that's why we have that other black part. But if you have dense and sparse, this is a subset of sparse. This is this max degree condition. That's a subset of sparse graphs. Yeah, and so the classification here would be, so we have a sequence of Gn, let's say it converges to W, and we take the line graph of Gn, L of Gn to be Hn, and let's say Hm converges to U, so W and U are graphons, like defined on the unit square. So if Gn is in dense, if you're here, then W is not zero, because you've got a graphon, like standard graphon, but obviously you're not here, you're going to get a U to be zero. So examples like Erdős-Schrödinger graphs are here, are in the dense space, and your U is zero. If you're in sparse, if you're not in S sub x, so if you're here, then still your U is zero. Your W is zero because you're sparse, and your U is also zero because you're here. And then like these are like parts and cycles, like you have like A connected to B, B connected to C, C connected to A again, like, the cycle graphs, these are all in here. There's a lot of stuff over there. If you're in S sub x, which is this max degree graphs, then U is not equal to zero. What are the graphs that are there? Superlinear preferential attachment graphs are there, and stars are there as well. Right. Basically, if you have these very strong hubs that are growing like, at a certain rate, then they're there. So again, this is like another mapping where your GN is, where your HM is. If your GN is here, then your HM is sparse over there. And if your GN is there, then SM is still sparse. But if your GN is there, if your original sequence GN is there, then W0, U is not zero, right? So that's just another view, how the GNs and the HMs map to each other. Now to talk about mixtures. So this is all good, but we know something about it. And before talking about mixtures, I want to talk a little bit about these line graphs and their inverses, because we will talk about inverses a bit. All graphs are not line graphs. The graph space is massive. You have so many graphs, but only to be a line graph, there are like conditions that need to be satisfied, because your edges have to be mapped to the vertices. So there are 9 line forbidden graphs. So there are 9 graphs that cannot be an induced subgraph. If they're an induced subgraph, then that's not a line graph. So it's very easy to break the line graph property, right? It's very easy to break that property. So also, if 2 line graphs are isomorphic, then their inverse line graphs are also isomorphic, apart from one exception. And that exception is a very simple exception, that the line graph of a triangle or a line graph of a 3-star are both the same. That's the only exception. Everything else, 2 line graphs isomorphic, you can get the inverses. And then if a graph is a line graph, then there are these algorithms of big O n complexity to compute the inverse. People have done that this started in 60s, 70s, people are doing that, and then it stopped, people didn't do that anymore, right? Yes. The inverse part, the inverse algorithms. So Now, we were looking at these max degree condition graphs and wondered, what are these line graph limits? Can we originally started with, okay, an Erdős-Schuoni graph, can you compute the inverse line graph of that? And how many modifications do you need to do to compute the inverse? And for Erdős-Schuoni graphs, we had to do so many modifications, right? We kind of knew this cannot be a line graph, but is there like somewhere proved to say. Then we found this theorem by Janssen in 2016, this paper, graph limits and hereditary properties. A graph limit is a line graph limit if and only if it is a disjoint clique graph. So line graph limits can be only like that. So it doesn't need to go from one end to the other end. There can be empty bits, but it needs to be like that. That's a line graph limit. So the interesting thing is previously Graphons had the gray parts, but for line graph limits, the gray parts are not there. It's either black or white. So, you're going to flip a coin, either you're going to, that edge, the probability is 1. And so the stochasticity is kind of gone away with the line graph limit. So what does this say? This says, okay, the line graph limit, you can only get disjoint cliques as the graphs, and the inverse of disjoint cliques are stars. So the inverse line graph exists when you sample from a line graph limit, and they can only be disjoint stars. There's nothing else in there. So in the graph limit space. So that's like, oh, okay, I thought there'll be a lot more in the, these just when you take the line graphs, but now in the limit, you're only going to get stars. There are other line graphs, of course, but in the limit, when you sample and compute the inverse, you're going to get stars. So what we do is we propose mixtures. So before going into mixtures, let me remind you, so given this Graphon here, there's a Graphon here, we have this Rij. We sample, the way we sample from a Graphon is we sample n random points, R1 to Rn, and for every Rij, we read this Wrij, which is just underneath the picture there, and then you toss a coin with that probability and connect the nodes. So if with this Graphon, where for n equals to 10, this is the graph I will get, and this is another graph that I got when I used n equals 20. So you can generate graphs of arbitrary large and large sizes from a given graph, right? So the Graphon mixture is you have a dense Graphon and a sparse graph. So the dense Graphon, you sample a graph like this. So you have some number nd, the number of dense points you sample. And for sparse, you have another number. First, you sample the disjoint cliques and then compute the inverse line graph, which means those are the stars. And then you randomly join them. Randomly join them in the sense we can have like a number of edges, like a number of edges that we give as a budget to join, and you join any node here randomly with a node here, you have like a limit on the edges that you can add, right? So you have the parameters are the number of dense nodes and the number of sparse edges, ms, because this is a dense Graphon. It's only when you compute the inverse line graph that you're going to get the sparse part. And then you join them. This here, in this example, I've used the dense number of nodes to be 20 and the sparse number of nodes to be, dense number of nodes to be 50, sparse number of nodes to be 20. And you sample a graph here, that's the graph, and you sample the graph there with 20 nodes, that's the graph, you join them. It looks more dense because there's more edges. But in this example, if I use 50 dense nodes and 100 sparse nodes, the stars are more prominent and you get this more star-like pattern there, like in a sense, more stars join. So this is the mixture that you have. And depending on this ratio, NSI over NDI, so this is the number of nodes in the sparse, number of nodes in the dense, If this limit, if you take the ratio and take the limit of that ratio, if that limit goes to infinity, then our sequence is sparse. If you take the limit of the ratio, if it is bounded, it is dense, because you're putting more from dense in here and you're putting more from sparse in there. So if you put more bigger and bigger stars as you go, then you're going to get a sparse graph there. But if you make more parts from the dense, you're going to get a dense sequence. So these are some experiments that we've done where you have these are experiments where NSI over NDI change slightly in different ways. You can get the dense ones so this is the edge density for a sparse graph. The edge density goes to 0 and you can change it. How quickly it goes to 0, you can change with this sequence. And so this way you can generate sparse or dense. And now, what about inference? If you are given a mixture graph, can you infer what are these different components? So if given a UW mixture graph, can we estimate U? We didn't look at estimating W because there are all these other methods to estimate W, and U is the new thing that we're introducing. So we focused on U. We can estimate U if the graph sequence is sparse. If it is dense, then it's not really that clear. In certain cases, you might be able to, but you might not be able to as well, because the dense part can drown the sparse part. But if it is sparse, you can estimate U. And it's the degree distributions that show us, because from here, I wish I can, this is that Graphon with 3 blocks behind the thing there. So this is the degree distribution. The degrees on the horizontal axis and the frequency, and you have you see a power law log kind of a plot where you can draw a line. Here what you have is so in this one I'm ranking I'm plotting the log degrees, but this is the degree rank. So this is the top highest, second highest, third highest, and so on. So you see this part here, the top 3, because you have those 3 blocks behind the, in the Graphon, those are generated, the 3 top degrees are generated by the sparse part. And you can estimate that by fitting 2 lines, one to here and one to there, you can get the elbow point and estimate your U. So basically those 3 come from U, the top part there. And you can plot a thing and then get the number of components there. That is the number of partitions. So U doesn't need to be like a 2D thing. It can be represented as a vector, P1 to Pn vector, and it can be an infinite partition as well. And your P hat is actually the degree, the jth degree divided by the sum of the components of that part. Right, so and we can have certain bounds on the expectation, these are error bounds and the various bounds and things like that. So you can have just finite partitions for P, because you can be given by this partition P. You can have an infinite partition P as well, and we show that in these cases the estimate K, which is the number of components, increases as the graphs grow in size. And these P's are kind of giving what are the big players in the network, and in a way they influence as such. So we can also, so given a sequence of graphs, and if you say, oh, for the next graph that has 1,000 nodes and we've only observed 500 nodes, what are the degrees going to be like? We can estimate the degree of the kth hub. And it is a very simple estimation that we can do, and then we can get error bounds on these as well. So the degree distribution can be estimated. And in the paper, we show that, that our method performs better compared with some of the other methods. So So these mixtures are a simpler method to generate sparse graphs using inverse line graphs, because like all the other methods were somewhat more complex because the graphon goes to zero. But using the line graphs and inverse line graphs, we can generate these mixtures very easily. We can generate either dense or sparse graphs. And this also has this motivation. These real networks have these high degree hubs forming the skeleton and low degree vertices constituting the body of the network. So the UW mixtures like have this property. We have these big hubs and then everything else gets connected. And the flexibility where we can get dense or sparse, and then we can infer U and predict the top K degrees as well from here. So this is the R package is still on GitHub. I have put it to CRAN, but I've got to do some modifications here and resubmit. So this is the sticker where we have the dense graphon, the sparse graphons in a jug, and out pours the mixture graph. Is that a thing? But and it's called Graphon Mix. The other types of join, like right now we've used random joins. Maybe other types of joins are better, or maybe like right now these mixtures scales, the hubs degree scales linearly. How do we incorporate other rates? And then coding, like having neural networks to represent the graphon. So I've seen some work where neural represent, so the people train the neural network to represent the dense graphon, but for the sparse graphon, they haven't really done the work possible because the other methods are like slightly more involved. And so sometimes they've used sparsification, but like, I think with the mixture model, we can do something where the neural networks can represent these mixtures where you see them and you learn the neural network. And that's about it. So give it a go with the Graphon Mix R package, which is right now on GitHub, will be on CRAN soon. And thanks so much. Thank you very much, Mrs.